Hello everybody, and welcome to Lecture 3 of Environmental Sciences 347, Introduction to Climatology. In this lecture, we're looking at the planetary energy budget, and to do that, there's three fundamental things to take home from this. First is to understand the electromagnetic spectrum. Second, to understand how solar energy interacts with the Earth system. And finally, the role of the atmospheric gases in regulating the planetary temperature. And this is all in the much larger scale. We're not going to be examining why one part of the world is warmer than the other, at least not just yet. But right now, we need to take a step back and look at the big picture on how the temperature budget of the planet plays out. So to start with that, we have to go back to basics with the electromagnetic spectrum. There are several forms of electromagnetic radiation, anything from very high energy gamma rays to much lower energy radio waves. And it's important to remember that what we see with our eyes is a very teeny tiny part of the overall electromagnetic spectrum, what we call visible light. And it does run the gamut. Here's a closer look at some of the wavelengths and frequencies that go with the electromagnetic spectrum, all the way to the very far left, which are very low frequencies, to the far right, which are very high frequencies. And as you might guess, these very high frequencies, low wavelengths, have very high energy, things like cosmic rays, gamma rays, and X-rays. And then falling off the curve, if you will, from right to left, we get to the ultraviolet and then the visible spectrum. Then going beyond that into these longer wavelengths, we get to the infrared and then microwaves. Microwaves actually have less energy than visible light. And then farther below that into lower energy microwaves or higher energy radio waves. That's where your cell phone band is operating. And then once you go to much lower frequencies, you end up with radio waves. But important to remember that the lower energy waves, when we look at the visible spectrum, are the infrared. The higher energy waves are the ultraviolet. Another way to look at it here, again, you see on the far right, as those waves are smashed together, those are the high energy, very short wavelength gamma rays, and then going from right to left, decreasing energy, and to radio waves. So radio waves can travel a very long distance. That's why radio stations travel a very long distance. But gamma rays do not. Those can kind of interact with the So here's another way of looking at them with the lower energy waves to the left, the higher energy waves to the right. And this is why we have higher energy particles like X-rays taking images of your bones. This is why we don't spend a lot of time in tanning booths or in X-rays because repeated exposure to those can start to cause problems with your skin. They start to mess up with your DNA a little bit once you get to the very high levels of radiation. Whereas you go to the lower energy particles here, the lower energy waves, microwaves, radio waves, they're not going to bother you too much. The wavelengths are too long and the energy is too low. So sometimes you'll hear the term black body tossed around, and this is kind of a theoretical maximum. When we think about a black body surface, we're imagining any kind of body, if you will, that sits at a constant temperature, which absorbs all the radiation that's incident upon it and then emits it pretty much all back. So if you're bringing all the energy in and then sending it all back, that means there's no net gain of energy. So your temperature basically remains constant, but it's a perfect absorber and perfect emitter of radiation. So the black body, sometimes we think, oh, it's a black body, so it's taking in everything and getting hotter. When we're talking about things in the electromagnetic spectrum, We're talking about things that perfectly absorb and perfectly emit at the same time, so that there's no net change in that body's temperature. Now, the other thing to think about, and this is kind of intuitive when you think about it for a while, using the black body as an example, we use Wien's displacement law, basically saying if something is hot, it is giving off radiation that peaks at the shorter wavelengths. If it's not hot or cooler, the radiation peak is at longer wavelengths. So going back to what we said before, things that are hotter are giving off more energy, so higher energy waves, compared to the lower energy, cooler things, so lower energy waves. So for this example here, the maximum amount of radiation goes with the temperature. And it is not a one-to-one correlation either. The short version here of the Stefan-Boltzmann law basically says that the amount of energy goes with the fourth power of the absolute temperature. And the absolute temperature is back to the, not really degrees, but they're called kelvins, where absolute zero on the Kelvin scale is zero. That's like about minus 450 degrees Fahrenheit. But the idea here being, and the important thing to remember, is that energy is not proportional directly to temperature. All right? Energy goes up to the fourth power of temperature. So if your temperature goes up 2 units, your energy goes up 2 to the fourth, or 16. So energy goes up dramatically for a small increase in temperature. Reverse that, thinking about how far away an object is from an energy source. It's the inverse square law. It kind of works backwards. The farther you are away from an object, let's say you're twice as far away from an object that's giving off energy, the sun, all right? If you go twice as far away, the energy loss isn't twice as much, all right? That goes as the square of that. All right, so for the example on the bottom there, you see at a distance of 1, let's say you're getting 100% of the energy from a particular object. But then if you double that distance to 0.2 there, do the inverse and square it. You've got 1/4 of the energy you had. All right, so 0 to 1, you're still getting the full energy, but you decrease that, you double it, you're now getting not half, but 1/4 of the energy that you got before. All right, so instead of going from 1 point to doubling it, which you would think would be 1/2, no, you square that number. You square 2, you get 4. So you're getting 1/4 of the energy you got just because you doubled the distance. So let's go back and think about the sun, because that's what gives us all of our energy, at least initially. And 3 things to remember about the sun. The visible part of the sun is called the photosphere, photo meaning light. So the visible part of the sun is called the photosphere. And you know, with a good telescope and a safe telescope with the right filters, you can see relatively dark, cool spots on the sun, which are known as sunspots. Now, outside of the immediate photosphere is the chromosphere. That's hydrogen and helium ions running around. And then beyond that is the corona, the sun's outermost portion. And that's a region of exceedingly hot and rarefied ionized gases. But for most of our purposes, we're interested in the photosphere. And the corona is something that generally is not visible, with the exception of the time during a total solar eclipse. If you saw some of that back in 2017, you might have seen the corona. Another thing that's intuitive, you might remember from grade school, is the angle of the light onto the source. All right, so when we think about the solar angle, the angle of the sun above the horizon, that goes a long way in determining how much energy you're getting from the sun. The flashlight over a black surface is the classic example. If the flashlight's directly over a perpendicular surface, all the light is focused in on that one surface, all right? But if you hold it in position B there, you still have the same amount of energy coming out of the flashlight. However, that energy is now distributed over a broader area. Okay, so again, think about position A, the sun directly over the equator. Think about position B as the sun where it is here in the middle latitudes. And you can kind of nudge it up between A and B depending on whether it's summer, fall, spring, or winter. So looking at that from another angle, the solar radiations path through the atmosphere in addition to the actual angle of hitting the atmosphere determines how much energy gets to the surface also. Because the energy from the sun has to interact with the atmosphere before it gets to the ground surface, whether it's land or ocean. And in that top example, because the Earth is round, the solar energy has to go through more atmosphere at that top position, position Y, than it does at position X. So not only is the energy distributed over a broader area, there is more refraction or diffusion of the energy at a higher latitude, closer to the pole, because just from geometric arguments, there is more atmosphere you have to get through before it gets down to the surface. So you think about this, and it translates into the seasons. When you think about the rotation of the Earth on its axis, accounting just for day and night, the orbital eccentricity, or how circular the orbit is around the Earth, because it's not a perfect circle, it's more of an ellipse. And then the tilt of the Earth on its axis. Right now, the Earth is tilted about 23.5 degrees from the vertical, and it stays on that fairly consistent axial tilt all the way around the sun. It doesn't wobble around the sun through the course of a 12-month year, right? It stays in that one direction as it goes around the sun. There are two nicknames for those times during the year where the Earth is closest and farthest from the sun. Perihelion is the day when the Earth is closest. Aphelion is the day when the Earth is farthest from the sun. And it's a little bit counterintuitive because there is still some thinking out there, it's wrong, that we have summer when the Earth is closer to the sun, and that's not the effect at all. We have summer in the northern hemisphere when the sun's actually farther away. This has everything to do with the tilt of the sun, or tilt of the Earth toward the sun, versus how far away it is. And the difference is about 3 million miles between summer and winter. But part of the reason why we're not warmer in the winter or hotter during the summer is because even though we are closer to the sun in the winter, and so the southern hemisphere is getting more energy, southern hemisphere also has more ocean than the northern hemisphere. So that kind of balances things out because it takes a lot more energy to heat up water than it does land. So when we're in winter, the northern hemisphere, southern hemisphere is in their summer and they're closer. So you would think, well, their summers would be hotter, but they're not, mainly because there is more water in the southern hemisphere. Just a reflection or a remembering of some of the astronomical seasons and the terms that come with them. The equinox is basically, it's an old term meaning equal night. The sun's position is basically over top of the equator. Solstice is the time during the year when the sun is at its maximum poleward extent in the sky relative to the equator, 23.5 degrees north or south. So the summer solstice for us in the northern hemisphere, the sun is, apparently from our vantage point, is directly over top of the Tropic of Cancer. The reverse is true for the winter solstice in December, where the sun is directly over the Tropic of Capricorn in the southern hemisphere, 23.5 degrees south latitude. So when we examine how much energy is getting into any one place on the Earth regarding its latitude, you see this curve here from January to December, going from left to right, from the vernal equinox, or what we think of as a spring equinox in the northern hemisphere, to the summer solstice at the end of June, the autumnal or fall equinox for us toward the middle or latter part of September, and then the winter solstice right before Christmas. So that most solid line is the amount of daylight in Edmonton, Canada. During January and December, it's very, very low, but during the summer, you get a lot more. Conversely, you go to Caracas, Venezuela, and at 11 degrees north latitude, there is a little more daylight during the summer than there is during the winter, but not as much of a variation because they're so much closer to the equator. And this is just one of those geometry things. You know, the Earth is tilted on its axis, it's round, so different parts of the Earth are going to get more daylight at different times of the year, depending on their latitude. So how much energy is coming from the sun? There is a quantity that's defined as the solar constant, even though it has some very small fluctuations depending on how active the sun is at any given time regarding sunspots and the like. But it's defined as the rate at which the solar radiation falls on 1 unit area of a flat surface, technically located at the outer edge of the atmosphere and perpendicular to the incoming sunbeams, when the Earth is at its average distance from the sun, meaning between aphelion and perihelion. So that's a lot to take in, but you think about how much energy is coming in per square meter at the top of the atmosphere. In other words, how much energy is coming from the sun per square meter when it gets to the atmosphere before that energy starts to interact with the atmosphere and become diffuse. So right now that value runs at about 1,366 watts per square meter. So that's a lot of energy in a very small area. And this chart here, on the left in particular, shows you how solar radiation changes by latitude during the course of the year. In other words, if you think about the day of the year, the first of the year here at the left, and the end of the year on the right, and the latitudes here north to south, up and down on this particular chart. Down there at the bottom left, that's where the sun is out all day long and all night long, 24 hours at the South Pole, the 1st of January. But at the North Pole, there's no sun at all on the 1st of January. And you start to see this relatively high level through most of the southern hemisphere. Then as we go forward in time, approach the June equinox, summer equinox, it shifts. Now there's nothing. There's no solar energy getting into these very high latitudes near the South Pole. And the sun's up all day long, all night long here at the North Pole. And you have the variations in between. So you can kind of trace out this curve, or you can think of as the effective equator, if you will, as the year goes on. So we talked about the energy getting to the top of the atmosphere, if you will, before it starts interacting with the molecules in the atmosphere, in the air in the atmosphere. So once that solar energy or solar radiation gets to the atmosphere, it starts to scatter, which means it can start dispersing in many directions, or just reflect. In other words, it hits some interface and then bounces back. All right, so these are the two primary things that happen to solar radiation when it starts to get to the Earth. It can scatter or just reflect, which is kind of like backscattering. The fraction of the radiation that is backscattered reflected if you will, is known as the albedo. All right. One of the most interesting things that I've seen regarding scattering or reflecting or what have you is how solar energy interacts with water droplets or ice. These are two pictures that were taken at the same time. I was driving north on Interstate 85 in North Carolina. It's years ago now. All right, and it was a day or so after an ice storm. Roads were fine, but there I'm driving north, and if you look at the trees just, they look fine. It's the dead of winter. There's nothing on the trees. But then we turned around and looked out the back window, and you could see the glistening of all of these trees because there was still ice on them. So in this first shot on the left, the sun is behind us. The sun hits the ice crystals and then refracts forward, or what we call forward scattering. All right. But in the southbound one, where we're turning and looking back toward the sun, in the direction of the sun, not right into the sun, but at least in the general direction of the sun, that sunlight hits the ice and then scatters forward toward me. And that's why we start to see this glistening in the trees, especially here on the left side of this picture on the right. So the sun is in that general direction. I'm looking toward the sun. Sun hits the ice crystals and liquid water drops on the ice, on the trees, and then that sunlight refracts forward, scatters forward toward my eyes, where that's not the case on the one on the left. It's scattering away from me. So let's talk about a couple other things that can happen with the atmosphere and solar radiation, in addition to scattering or refracting. It can also be absorbed, depending on what kind of radiation we have. This absorption is the process, if you will, where energy is converted as the radiation strikes an object and is converted to heat. Oxygen, ozone, water vapor, other aerosols in the atmosphere absorb solar radiation. And aerosols is still a term that we often think about those cans that spray stuff. But an aerosol is any kind of particulate matter in the atmosphere that is suspended. Salts, smoke, things like that. A lot of times they're too small to be picked up with the naked eye. But those are called aerosols. Things are solid or liquid particles that are suspended in the atmosphere. But because the atmosphere is made of different gases and there's different stuff in the atmosphere, the absorption varies by the type of wavelength of energy that is coming off of the sun. Now, the sun sends out energy in all wavelengths, but some more than others. And we'll come back to that in just a second. You've heard of ozone. The stratospheric ozone shield is what effectively helps life on Earth thrive. There is the greatest concentration of ozone. And remember, ozone is O3. It's oxygen with 3 molecules of oxygen. Most of it sits up about 25 miles up, as we talked about at the beginning of the course, up toward the stratosphere. And there are chemical reactions with ultraviolet light that are involved in creating and destroying or dissociation of ozone that kind of keep that level of, or that amount of ozone in balance. And it doesn't remove all ultraviolet, but it removes the worst of the ultraviolet because there's ultraviolet A, B, and C. And each one of those is a little stronger than another, has more energy. So to produce ozone, ultraviolet will hit a regular oxygen molecule, O2, dissociate it. So you've got 2 oxygen atoms running around, and then they will bump into another oxygen molecule and, I say fuse, but effectively combine or bond, not really fuse, but bond, and give you 2 new ozone molecules. But then the reverse also happens. You've got an ozone molecule, ultraviolet light will interact with that, effectively strip off the bonds of one of the oxygen atoms. And then you've got more diatomic oxygen running around as well. So this process is always in motion in the stratosphere at a relatively steady state. That's why we have a reasonably constant amount of ozone in that part of the atmosphere. Again, 25 miles up. Many years ago, in the 70s, when chemical propellants were very popular, things that were called chlorofluorocarbons, it was discovered by NASA that those were getting into the atmosphere and sticking around for a very long time and kind of congealing, if you will, down toward the Antarctic. And that was the discovery of the ozone hole, if you will, in the Antarctic. So the ozone hole is the thinning of the ozone layer to significant levels since 1979. So those lines you see there are the ozone concentration since the late 1970s. And at the beginning of that graph, there was a big drop. So we're losing ozone there pretty quickly. Then the nations of the Earth decided to come together in something called the Montreal Protocol to stop producing CFCs. So while the ozone hole hasn't repaired itself yet, it has stabilized, and by all expectations, it should repair itself in the coming few decades. So that is a testament to finding something that went wrong and fixing it, coming together and fixing it. So backing up a little bit to talk about the Earth's surface and solar radiation. The direct solar radiation is that's passing through the atmosphere that gets to the Earth's surface. Again, some of the radiation that's not interacting with the atmosphere too much, it's getting through the molecules and getting down to the ground. And most of that is visible light. And that's why we see things, bringing sunlight, casting shadows. Diffuse solar radiation is scattered or reflected. And when we think about diffuse solar radiation, imagine a cloudy day where you don't see the sun, but it's not dark outside. There is sun that's getting through the clouds, just not directly. It's hitting the clouds, diffusing on all directions, and you don't really have shadows. I mean, you can see just fine, it's cloudy, but there's no real shadows because you don't have direct solar radiation, you have diffuse solar radiation. So the direct plus the diffuse striking the Earth's surface can still be reflected or absorbed depending on the surface albedo. And the albedo is a characteristic of the surface that shows the reflectivity of it. Here are a few examples of different surfaces and their albedos. Things like deciduous forest, conifer forest, tropical rainforests, they absorb a lot, so their albedos are very low. But things like a fresh snow, very high albedo. They reflect a lot. Glaciers reflect a fair bit. Water, the reflectivity of that depends a lot on what the solar angle is. Clouds have different albedos, whether they're cumulonimbus clouds or cirrus clouds. Cumulonimbus clouds are a mixture of liquid water droplets and ice. Cirrus clouds are entirely ice. Deserts, sands, they have different albedos. Grassland has a different albedo, depending on specifically what type of grass, what type of plants are on the ground. But the short version is grasslands, forests, they absorb. They're absorption. They absorptive, if you will. Ice reflects. Now, back to what we were talking about before in terms of what kind of energy is getting through the atmosphere. The atmosphere is relatively transparent to visible light, all right? But it is not transparent to all types of electromagnetic radiation. Talking about infrared, ultraviolet, and those kinds of things. Water, for example, is absorbed by longer wavelengths of light more effectively than shorter ones. So the reds, the yellows are absorbed, and that's why we see blues and greens left over, remembering that white light is a combination of all colors in the spectrum, or the rainbow, if you will. So if you absorb reds and yellows, what's left? Blues and greens. And that's why the open ocean, anyway, tends to look to us as blue or green. Here's another version of that on the bottom. So the reds, oranges, and yellows are absorbed fairly high up, and the blues and greens can penetrate a lot deeper into the ocean before they are absorbed. Top one there shows the albedo of a flat and undisturbed water surface, something without waves, under clear skies. So as the solar altitude increases, all right, the albedo of a flat surface decreases. So through lots of painstaking measurement over the years, the global solar radiation budget plays out this way. When you look at the Earth, atmosphere, land, ocean, cryosphere, all that combined, right? That system reflects back to space about 31% of the solar radiation intercepted by the planet. And that's known as the overall planetary albedo. But obviously, it's not constant across the whole planet. Different parts of the planet have a different albedo. As you might guess, polar ice caps, they're very highly reflective. Things like the Amazon forest, very low reflective. So for the whole system, we look at about 31%. Half of that is absorbed by the Earth's surface, okay? But 20% is actually absorbed by the atmosphere. Again, not every wavelength is absorbed in the atmosphere. So when we think about the energy that does get through the atmosphere back down to the ground from the sun, because the atmosphere is fairly transmissive to solar radiation, most of it just gets through. The sun doesn't heat the air very much at all. Most of the energy is getting through the atmosphere down to the ground, all right? So as that solar energy heats the ground and starts to emit, all right, it heats up the atmosphere from below. So that's why the warmest part of the atmosphere is at the bottom. Sun's not heating the atmosphere very much. The short version is that the sun heats the ground, and then the ground heats the atmosphere over top of it. And that works at night as well. When the sky is clear and it's wintertime, the Earth is giving off all of its energy it took in during the day and sending it back out to space. So if all these things are kind of in balance, we reach a radiative equilibrium. So the average temperature of the planet doesn't change. So the outgoing emission of heat to space in the form of infrared balances the incoming solar from the system, from solar radiational heating from the Earth system. So in other words, incoming solar balances outgoing terrestrial or outgoing infrared. When those things balance, we're in a radiative equilibrium and there's not a temperature change. Again, in the mean for the whole planet. Now, back to what those specific gases are doing, what we call the greenhouse effect. The heating of the Earth's surface at lower atmosphere caused by strong absorption and emission of infrared radiation by certain gases. In other words, certain gases in the atmosphere, very, very small amounts, are known as greenhouse gases because they're very active in what we think of as the heat part of the electromagnetic spectrum, the infrared part of the spectrum. All right. This is similar to what happens in a greenhouse. Not exactly the same thing, but there's a similarity. At a greenhouse, you've got solar radiation coming in, heating a surface, but you're not letting any of that energy out of a enclosed area, so it warms up, as opposed to in the planetary greenhouse effect, there's actually heating going on by the gases that are enveloping the planet. So it's similar. It's a reasonably good analogy, right? So what you see there on the bottom right is the absorption spectrum of several gases into the atmosphere. All right, I'm going to zoom back in on that in just a moment. But the important thing to see here is that there are peaks and valleys and different gases and different wavelengths to show that there are some parts of the atmosphere that are very transmissive to certain wavelengths of the EM spectrum, and some that aren't. Like, for example, if you look at all that blue on the left part of that graph, that's UV, which is almost entirely absorbed by ozone and oxygen. Not all of it, but almost entirely. I mean, you stay outside long enough in the summer, you'll get a sunburn. Staying outside long enough in the winter, you'll get sunburn, but it takes a lot longer. Why? Well, because the sun is a lot higher in the sky in the summer than it is in the winter, so you get more direct sunlight on you as opposed to during the winter time. So what are these gases? Water vapor is actually the strongest greenhouse gas. And I think that gets lost a lot. But the thing about water vapor is that it's really easy to get out of the atmosphere in the form of rain or snow. The other important greenhouse gases are carbon dioxide, methane, and ozone. All right, but there's very little ozone averaged throughout the whole globe. It's at a very small concentrated layer, 25 miles up. That's very important. But in terms of a heating contribution to the atmosphere, it's pretty small. Okay? And that kind of leaves us with carbon dioxide. So back to this other chart before. Let's slice this up into its 6 layers from top to bottom. That's CH4, methane, the nitrous oxide, ozone and oxygen, carbon dioxide, and then water vapor. Each one of those layers. And then that bottom layer is the top 5 all combined. All right. Then on the horizontal axis, we're looking at ultraviolet energy through visible light through the infrared part of the spectrum. So for example, like I said before, look at that third one. All those blues on the far left are showing you that, wow, look at that. That's underneath of the UV. So O2 and O3 are absorbing almost all of the ultraviolet light that's coming in from the atmosphere. Just to the immediate left of that is the visible window. That shows you that methane doesn't absorb visible light. Nitrous oxide really doesn't absorb visible light. Oxygen, ozone, a tiny, tiny bit. But CO2 isn't absorbing visible light. Water vapor isn't absorbing visible light. So that's why we can see stuff. But then as we go to slightly higher wavelengths, the gases in the atmosphere begin to interact with those wavelengths differently, especially carbon dioxide and water vapor. You see the big peaks there, CO2 and H2O. All right, and there are some places looking at between 2 and 3 micrometers on the bottom part of the chart. And again, 6, 7 micrometers, where the atmosphere is effectively opaque to that level of infrared radiation at that specific frequency / wavelength. But there are other parts in the infrared that are almost perfectly transmissive, if you will. And those are called the infrared windows. So it's not everywhere in the infrared that the atmosphere absorbs energy, but a lot of it. And especially as you go to the higher wavelengths, 20, 30, 40 micrometers, that is almost entirely absorbed. So sometimes you hear about the infrared satellite picture in weather. We tune those satellites to look at those atmospheric windows. so that we can look for water vapor, we can look for clouds that are closer to the ground that are emitting at those wavelengths. But a lot of that is getting through the relatively drier part of the atmosphere above it. Remembering that the troposphere, that bottom part of the atmosphere, is where all the weather's happening. So by tuning your satellite to some of these infrared windows, 10, 11 micrometers, you can sense what's going on closer to the ground by that stuff on the ground emitting in the infrared part of the spectrum, 8, 11 micrometers, and that making its way through most of the atmosphere back up to orbit, so your satellite is up there receiving that energy, looking for it. Not actively looking for it, but can passively sense the infrared energy at that part of the electromagnetic spectrum to find things like clouds, because clouds are cold. So you're not really even sensing clouds so much as you're sensing temperature. And then you can correlate temperature to clouds and anything else on the surface as well. So to review this part, water vapor strongly absorbs outgoing infrared and emits infrared back towards the Earth's surface. All right, water vapor, a very important greenhouse gas. Greenhouse means it's very active in the infrared part of the spectrum. All right, but it doesn't instigate warming or cooling trends in the climate. Its role in climate change is to amplify rather than trigger climate trends. All right, and then when we think about water in the form of clouds, because clouds are liquid water droplets and or ice. Water vapor is invisible. Clouds are liquid or solid water. All right, and they work in two different ways. One, to warm the climate by absorbing and emitting in the infrared, but also cooling by reflecting the incoming solar at the top of the atmosphere, if you will. All right, so once that energy gets into the atmosphere, it kind of bubbles around, works itself around. But if you think about how clouds look from above, you look at the classic daytime satellite images, the clouds are white. Solar energy is bouncing off the top of the clouds. That's why we see them. So with that, a little introduction to climate change here, developed by Guy Stewart Calendar effect. He kind of put forth the theory that global climate change could be brought by enhancing the natural greenhouse effect by increasing CO2 from burning fossil fuels. Now, there were other scientists before him, which we'll touch on later in the course, that understood that carbon dioxide was an active gas in the infrared, that it would raise the temperature of the planet. All right, and this was known for more than 100 years before Calendar came along. But he was the first to say, you know what, we could actually change, we could physically change the temperature of the planet if we continue to do these things. This is the greenhouse gas index to show which gases are most important, which are doing the most work, if you will, called radiative forcing. Which gases are contributing the most toward the anthropogenic or the man-made greenhouse effect. And the light blue there is CO2. And as we've gone forward since the late 1970s, that component has become greater and greater. All right, methane is held about the same, nitrous oxide is held about the same, but we continue to put more CO2 in the atmosphere. So that is a more important contributor to the overall planetary warming. Methane is important, nitrous oxide is important, all right? But we're seeing more and more CO2 going to the atmosphere and staying in the atmosphere. Things like nitrous oxides, things like methane tend to work their way out of the atmosphere more naturally, more quickly than CO2. Carbon takes a long time to get out of the sky. In fact, back in 1957, Charles David Keeling started a monitoring system, Mauna Loa in Hawaii, to monitor how much carbon dioxide was in the atmosphere. Chose Hawaii because at the time it was far away from other human impacts. You wouldn't want to monitor your CO2 in a place like Pittsburgh that has all these smokestacks, at least it did in 1957. Places that have a lot of industry that are punching out a whole bunch of CO2 every day. You want to go to some place where it's away from all that and the carbon dioxide can kind of diffuse and get well mixed through the atmosphere. All right, but that number's gone up from just below 320 in 1957 to pushing 420 today. So it's been up, and this is almost all has to do with human forcings. It's almost nothing with volcanoes. So the anthropogenic or man-made contribution to the buildup of atmospheric CO2 probably began a few thousand years ago as agriculture or farming began to become a thing with human settlements. But it was very, very tiny increase at first. It's the Industrial Revolution that started it up the slope that we know today. But considering how industrial our society has gotten globally over the past 60 to 80 years, and how much we still rely on the burning of fossil fuels for energy, has really made that number jump, especially the last 40 to 50 years. So, backtracking to the beginning of the lecture, we talk about the global radiative equilibrium and climate change. The Earth's mean temperature at the global level is in a relatively equilibrium. It's not cooling, it's not warming. All right. That depends on the solar constant, the planetary albedo, how closely the planet approximates a black body. I mean, if the sun were to suddenly get hotter, it hasn't, but if it were to suddenly get hotter, that's going to change the radiative equilibrium temperature of the planet. All right. If we suddenly change the albedo, melt all the ice off of Greenland and Antarctica, that's going to change the albedo. So changing any of these parameters are going to shift us to a new relative radiative equilibrium. And adding CO2 is another one of those things, and that's a man-made impact. So, different external and internal forcings, sun, albedo, greenhouse gases, can change the average equilibrium temperature of the planet, bringing it to a new steady state or an equilibrium temperature. But as those forcings change, the planet will continue to warm or cool. All right, if the sun were to suddenly get very quiet, which is not happening, but if that were to happen, we would start to see a net cooling of the planet. Again, it wouldn't happen in a week, wouldn't happen in a year. It would happen over the course of a few years, depending on how much the sun started to cool. But that's a very, very small amount compared to what we've seen recently. So you change the internal or the external forcings, and then you will change the mean temperature of the planet, what we call boundary conditions. All right, so that's a take-home message from today. Think about the albedo. You think about what the Earth's surface is made out of. You think about what gases are in the atmosphere. You think about how the atmosphere reacts to those gases and the incoming solar radiation. Those are all the things that go in to contributing to the heat budget of the planet. So that's the end of this lecture. Next time we'll take that one step further and look at the thermal response to the climate system. So we just talked about what the average temperature of the planet is, and all these things go into the average temperature of the planet. Next time we'll talk about why this part of the planet is warmer than other ones. All right, how heat energy moves around the planet, ocean currents, air currents, those kinds of things. So that'll be next time. So thanks everybody. We will see you for our next lecture next time.